I didn't draw a picture.
Can you do it? Now, hurry up. Go to the hall. Go to the hall. No, this is really important. This is really important work. Go to the hall. Last game. Come back, but.
Hey, Mr. Rose, can I get a drink of water, please?
Yes. Did you just like buy a water bottle?
Yeah, I had one.
I used it all up. You get that changes everything.
Where'd they go?
Savage.
No idea what you're talking about. Oh, yeah. Who's your favorite teacher?
I don't know what to do. I could turn it off.
Don't make him talk.
I have no power.
Yes. I think no one watches these.
I mean, if you want to do this properly,
No one watches.
I cannot exclude
Actually, I watched
other
it.
classes that we're
Well, yeah, Eloquent has one.
Yes, I can do that.
Who didn't show up, but really, don't know who was. I mean, eventually we got the number. They were just like around. Oh, my mom. So eventually we got like everyone. So. Okay, so number one. I don't even know how to do it. It's like the song. I didn't even know what no, it's like all the songs of the area. Yeah, I swear formulas. Oh, this was the thing that the X sub I saw. So I was like, what? Yeah, no, actually. I'll be with you. I'm going to bring it.
This one would be like negative 840 plus 840. I'd like to get
Oh, yeah. Wait, negative 840?
Because it goes over like to 8. That's like just 1. Oh, wait.
Someone please do 9, 10, 12, 13.
Are you talking about 19 or 18?
No, basically, yeah. It's 8, right? Times that.
Oh yeah, I researched them. They're used to count the number of partitions. Boiler numbers. They're used to count the number of partitions of alternating zigzag sequences. Something like that.
Wait, did Did we have to draw a picture? Because I didn't draw a picture. I just did it.
How did you do it?
I mean, I drew like one for like. You should draw one for like number 3. Yeah, like number 3.
You just do the picture in your head.
Just know what shape it is. Know what shape it is.
Yeah, like, because it kind of follows the pattern. Then it's like, you just, they'll shape, they'll see the one, do the fourth one, get the answer.
Mateo.
Yes.
Who did 10?
Okay, good. Let's talk about number 1. This is the integral from -2 to 1. of x squared plus 1 dx. All right, let's talk about this. What am I talking about? This is the answer. This is the problem. The problem is the limit as n goes to infinity of the sum from I equals 1 to n of 3 over n I minus 2 squared plus 1 times 3 over n. All right, so you have to be smart enough to look at this and to figure out what integral it represents. And it's like a little bit subtle actually. So if you try to think about it, well, personally, does this look like a Riemann sum to you? I think so, right? I think that this part looks like the delta x part, and this part looks like the f of x sub I star part. So if this is delta x and there are n rectangles, which there are, because we take the limit as n goes to infinity, then what is the total width of the interval? What must the total width of the interval be? 3, right? So yeah, so the width of the interval is 3. Okay, well, now I have to figure out what the function is. Well, if I sort of think about what's going on, there's a couple different ways to think about this. Whoever did this, what was this? Ethan that did this?
Yeah.
Ethan looked at this, and he generally, this is what he saw. He saw something is being squared, and then we're adding 1. So he thought of the function as being x squared plus 1. This is not the only way to do this, but this is a way. So if we think of the function as being x squared plus 1, then what kinds of things are we plugging into the function? Into the function we are plugging I times 3 over n minus 2, which led Ethan to the conclusion that we must have been starting over here at negative 2. And now the function x squared plus 1, which looks kind of like this, well, what if I was indeed taking the integral from negative 2 to 1 of this function? How would I do it? Well, I would do basically exactly this, right? I would go over here to negative 2. I would split this up such that delta x was 3 over n. And then each of these right-hand endpoints of the subintervals would be in the form negative 2 plus I times 3 over n. And I would be plugging those into the x squared plus 1 function. Get it? And since delta x is 3 over n and the width of the interval is 3, if I start at negative 2, I must end at 1. Raise your hand if you figured this out. You just kind of looked at it and you just worked backwards. Is this making sense? No, gotta go fast. Please pay attention. Next one, number 2, second try. Second try, Sydney. Now I'm taking the limit as n goes to infinity of the sum from I equals 1 to n of cosine pi over ni plus pi times pi over n. Well, again, if we kind of look at this, if we think of this as being the function and this as being the delta x, then if delta x is pi over n, then what is the width of the interval now?
Pi.
The width of the interval must be pi, right? Because if the width of the interval was pi, but I'm splitting it up into n subintervals, then each one would have width pi over n, right? It's really understanding what integration means, but kind of going backwards. All right, well, if each of these is pi, then Busis looked at this, and he sort of thought of this as being like the function was cosine. So if we think of the function as being cosine, then what kinds of things are being plugged into this function? Answer, things of the form pi over ni plus pi. Well, from his experience doing lots of integrals, by definition, what we're doing is I'm always plugging in pi plus some number of like delta x's. In other words, it looked to him as if I was starting at pi, and then each of the little subintervals are going to be pi plus like 1 times pi over n, pi plus 2 times pi over n, pi plus 3 times pi over n, etc., etc. Each one being like each one being of the form I times pi over n plus pi. And where do we stop? We stop, since the width of the interval is pi, we stop at 2 pi. And so this is I'm just gonna draw a generic function because I don't feel like actually drawing cosine. This is gonna be the integral from pi to 2 pi of cosine. Follow? Okay, I think these are hard. Cindy, does that help second time? I have actually another worksheet I'm going to give you guys a little bit later that has like a lot more like this, because I think this is the good way of understanding what intervals are. Okay, so looking back at these problems now, super rapid fire. Integral from negative 2 to 1 of the 4 function, that's just a rectangle, it's 12. Yes, number 4 is also just a rectangle, boom. Is the answer 4? Yeah, it is. Number 5 is a trapezoid, and the area of that trapezoid is 21. Good, love it. Number 6, semicircle. 9 pi over 2, beautiful and correct. 7, we did like one of like these in class, right? You just draw a picture and you figure out that the area is 5 halves. Here you get a little TP looking house thing. This has area 3. Picture very much not to scale. But whatever. You have to be able to graph 2 minus absolute value x, and this person did pretty much decently well. What is this? This is a semicircle which has been moved up 1. So yeah, this is like a little igloo thingy kind of ish. And that has area 2 plus pi over 2. Beautiful. This is a trapezoid with height a, smaller base a, and bigger base 2a. So that's 3 halves a squared. Yes. Now we get to the ones I thought were actually most interesting. This one that was all about transformations of the one integral that they gave you, which is that the integral from 0 to 1 of x cubed, that is 1/4. So if I know that that's 1/4, so if I draw a little picture of this, it means that shape basically has area 1/4. Okay, well if that shape has area 1/4, what can I conclude? Well then the integral from -1 to 1 the integral must be 0, right? Because every one of these negative rectangles is canceling out one of these positive rectangles. Cool? 12 was the integral from 2 to 3 of x minus 2 cubed. Well now, the function is moving over 2, but so are the limits of integration. So this person drew a picture, and then they just look at this and like, yeah, of course, it's the same area, 1/4. Is everyone okay with this? Just like what you guys did? Alright, 13, this is the integral from 0 to 1 of, well, it's the same shape, but now it's been moved up 3. So the simplest thing to do is just to draw a picture and realize that it's that little guy, which is 1/4, plus a 3 by 1 rectangle, so the answer is 3 1/4. 14, the problem was the integral from -1 to 1 of absolute value of x cubed dx. Well now if you graph that, it's that same shape, but now everything's positive, so you're just going to get 2 of these little guys, so the answer is 1/2. 15 was a really cool problem. This is 1 minus x cubed. The cool way to do this, in my opinion, is to draw it. If you make x cubed upside down and move it up 1, you get this shape. And what is that shape? Well, it's the square minus the shape I know to be 1/4, so it's just 3/4. An alternative way to do this is to split this integral up into 2 little integrals, right? This is a 1 by 1 box, and now I'm subtracting a 4. Does everyone understand what I'm talking about? Kendall, you good? Alright, 16 is pretty difficult. Oh, this person did it kind of a cool way. They took, interesting. This person took absolute value x minus 1, and then sort of like performed graphical cubation on this or something, right? And then it turns into this. Yeah, cool. I thought about it as the x minus 1 cubed graph with the absolute value x transformation performed on it, which like you guys did way back in pre-calc A, like deletes the left side of the graph and replaces it with a copy of the right-hand side. Does anyone vaguely remember what I'm talking about? Like a thing you do with Giles, like last year. Anyway, you eventually must figure out that this is the shape of the function that we're looking at. And so what is the integral from -1 to 2? It's going to be an upside down a fourth, an upside down a fourth, and then a positive fourth. So the total answer is -1/4. Cool? Alright, 17 I thought was the most interesting one. This person got 1/2. Anyone get anything else? Yeah, Ethan. 1/16. Oh, interesting. How'd you get 1/16?
I was just wondering, like, does the x over 2 cubed, does that equal x cubed over 8?
It does, but I'm integrating from 0 to 2 now, so that's what makes this kind of different, right?
And I pulled the 1/8 out.
Okay.
And then said that it's basically like a 1/4 times 0 to 1 x cubed.
Yeah, but the fact we're integrating all the way up to 2.
Oh wait, I don't know if it doubles. So like, I don't
No, in general it doesn't double, right? Because the function's getting way, way bigger on the interval from 1 to 2 than it is from 0 to 1. So you can't do that. Who knows what the fuck, right? But what is going on here? It's sort of like I mean, I agree with this picture, right? We're stretching the function out by a factor of 2, but we're also increasing the interval by a factor of 2. Why is this 1/2? Why do you think it's 1/2? Yeah, is this you? Who did this one up? Oh, this is you? Okay, explain. I don't know.
Oh, okay, so basically it's the same height that you would have had, because it's like x over 2 instead of x.
Okay.
Alright, so the total thing will have a height of 1, same as the regular function would with 1/4.
Okay.
But then your base is being like twice as long, so you'll multiply by 2 because like that's how a lot of shapes work.
That's how shapes work. Okay? Counterpoint to me.
Would be 1/4 because it's like it's basically like a 0 to a 1. For some, like the 2 sort of like cancels out that 2 sort of.
Samin says sort of maybe the fact that we're stretching the function out by 2, but also going out twice as long is sort of like is the same thing or something. I don't know. What do we think? Who's right? Samin or Yael? Sandeep, what do you got? What'd you say?
I said 1/2.
Why?
Basically, like, I did it the way Ethan did, but I think I did it.
Correctly?
No. No, but I did, I cubed it, I cubed it, like, took out the 1/8, and then, yeah, and then just kind
No,
of.
then nothing. Then you're stuck.
Yeah.
Yeah. Unless you just do all that, the whole thing. Yeah, so look, if we look at this box, I'm not getting the class participation required. Feels right.
We don't know.
What?
We don't know.
You don't know the answer?
Participate, it's just like, we don't know.
Oh, you just don't know. So this is hard, right?
Yeah.
Yeah, I think it's a hard problem. That's why I'm going over it really slowly. So, Mateo, what are your thoughts?
I just don't know.
What did you write in your paper?
I wrote 1/2.
But now you're torn between 1/2 and 1/4.
No, it's 1/2.
What?
No, I still think it's 1/2, I just don't
Still
know
you're
why.
just not sure why. Okay, so first let me summarize what Yael said, but I'll do it in like teacher authoritative way, so you'll like listen to me even though you didn't listen to her. Look at this box, right? This is ultimately the same shape. So I think this box, this part that she shaded, is still like 1/4 of that box, sort of like in shape, except that box has area. Has area too. This is exactly what she said. Except she said that's how shapes work. But I mean, that's pretty much it, right? That is how shapes work. What we did is we scaled this thing by a factor of 2. If in the other case, the picture we've been working with as our base looked kind of like this, right? And we were led to believe that this purple thing was 1/4 of that 1 by 1 square, right? But now this is still 1/4, but it's 1/4 of something which is twice as big. In my opinion, however, the best way to understand this is the best way to understand integration in general, and that is to understand it on a rectangle by rectangle basis. If we take a particular representative rectangle on this interval, what can I say about it in relation to a particular representative rectangle in the original? Suppose this is the ith rectangle. Suppose that's x sub I star. And that is x sub I star. What can I say about these two rectangles?
X of I star is twice as wide as the other X of I star.
Yeah, and they have the same height, right? Yeah, by the way this function works, if I'm splitting up, since I'm splitting up this rectangle into n subintervals, and the width of the interval is 1, then the delta x is going to be 1 over n. But here the width of the interval is 2. So delta x is going to be 2 over n. Mateo, is this a little bit more convincing? So now if I go to the ith subinterval in both cases, since it's essentially the same function, right? Because the interval is being spread out, but the function's also being spread out. When I go to the ith subinterval, the heights of the rectangles are going to be the same. But each of these rectangles are going to be twice as wide as each of these rectangles. So if you compare the ith subinterval to the ith subinterval, this ith subinterval is twice as wide, and so everything's twice as wide. Okay, here I got -3/4, looking good, same kind of logic as before. Here 0, and here 3/4. This is what you guys got? Okay, there was also homework due today, which is the problems in the book. Should we go over a couple of those? Yes or no? I think we don't have time. I say I'm gonna just collect this homework. And now we have another quiz.
Can you get like our faces all like disgusted on camera? How did you do that? I looked at couch chat.
Mr. Rose, should I turn off the camera?